Hello, let's begin our discussion of Chapter 20, a confidence interval for the mean. We need to recall some notation. We were using mu to denote the population mean and y bar to denote the sample mean. The whole purpose of constructing a confidence interval is this. We want to estimate the unknown value of mu, the population mean, based on the observed value of y bar, the sample mean. If you recall, the central limit theorem gives us some valuable information about the sampling distribution of a sample mean. In fact, the central limit theorem says the sampling distribution of y bar is modeled by a normal model for large enough n with mean mu and standard deviation equal to sigma over the square root of n. Here sigma is the population standard deviation and n is the sample size. Now we have a problem. We rarely know the population standard deviation sigma. In fact, if we knew this, we'd probably know the population mean mu, and we wouldn't need to construct a confidence interval. So we'll use what we do know, and that is S, the sample standard deviation, to estimate the population parameter sigma. This results in the standard error of y bar, which is S over the square root of n. So again, I'm using S, the sample standard deviation, to estimate sigma, the population standard deviation. It seems reasonable to form a confidence interval for mu with y bar, the sample mean, plus or minus our critical value z star times the standard error, which in this case is S over the square root of n. This should resemble the form of the confidence interval we saw before for a sample proportion. But a problem emerges with this procedure, especially with small sample sizes. And that's what we're going to look at using simulation next. This applet is called Simulating Confidence Intervals. Let's set mu equal to 50, sigma equal to 30, and we're going to be using S, the sample standard deviation, as an estimate for sigma, the population standard deviation, to construct a 95% confidence interval. So I've got the confidence level set to 95. We'll start with the sample size n equal to 20, and I'll have this construct a confidence interval for me. Here it is. It's shown in green because it succeeded in capturing the population mean of 50. So let's do this. Let's add 199 intervals for a total of 200. And here's what we end up with. Most of them are green, but a few are red, and these are the ones that fail to capture the population mean of 50. Notice there's a running total here. 94% of these 200 confidence intervals succeeded in capturing the true population mean. So let's add a few more. We want a total of 1,000 confidence intervals. And if I look at the running total now, 93.7% succeeded in capturing mu. And that's less than what we were expecting. We set our confidence level to 95, so I would expect that 95% of these succeed, and that's not what we see here. So let's do this. Let's reduce the sample size to 10. I'll reset this. I'll start with one confidence interval. Shown in green here, this one succeeded. Notice now the interval is a little bit longer or wider than before, and this makes sense because the sample size has decreased So we would expect this confidence interval to be a little bit longer. So I'll add to this to get a total of 1,000 confidence intervals, and now the running total shows 92.3% succeeded, which is even less than when the sample size was 20. So we actually have a problem here. We're not hitting the mark. We'd like 95% of these to succeed. And so the solution is to use a new critical value. Instead of our Z star, we'll use a T star critical value. So I'm going to switch to T. Let's go back to a sample size of 20. I'll start with a single confidence interval. This one happened to succeed just barely in capturing the mean. And if we add to this for a total of 1,000 confidence intervals, notice now we do hit the mark. 95.8% of these succeeded in capturing the true population mean. So let's switch to sample size 10. I'll start with a single confidence interval. Here it is. And if we add to this for a total of 1,000 confidence intervals, notice here 95.1% of these succeeded. And that's right on the mark. We wanted this to be at 95%. So this new T star value is helping us hit the mark. What it's doing, it's making these confidence intervals a little bit longer, a little bit wider, to ensure that 95% of them succeed in capturing the true population mean. So I'll have more to say about this in the next video. See you then.